All right, class. I just wanted to do like a real quick, just because we ran out of time in class, I just want to do some real quick examples of e to the x, right? So we know y equals e to the x means that dy dx equals e to the x, because that's what this function does. The whole purpose of this function of e, Bernoulli's constant, is that it's a function in which the rate of growth, slope, is in fact equal to the actual value of the function. We like this because this is exactly how we define exponential growth. It is in a case where growth, in fact, right, the rate of growth is directly proportional to how much you already have. That's what exponential growth is, and so this is what we have. Now, so this is the derivative of e to the x. Now, what if I do things that are a little bit more complicated? For example, what if I did y equals e to the tangent of x? Now that looks really weird, but it's not bad. All that means is that the derivative is still the tangent of x. But now we have to multiply by the derivative of what's inside, which the thing that's inside is the tangent, and so we get secant squared x. So that's pretty good. Or another example, so I'm just going to kind of rip through a whole bunch of examples here just to kind of let you see how this is working, right? So what if I have y equals e to the 3x plus 4? Well, that means y prime is going to be e to the 3x plus 4 times the derivative of what's inside, which in this case is just a 3. So it's going to, better written as that, right? So that would be our answer for y prime or dy dx. We can do kind of even a larger chain rule. Let's do something along the lines of y equals e to the square root of 5x. There we go. So, what is dy dx? Well, derivative of e to a function power is e to that power times the derivative of that power. Well, the derivative of a square root, if you remember, is that. But then we have to multiply by the derivative of what's inside the square root, which is that. In other words, we can probably rewrite this a little better as 5e to the square root of 5x over 2 square root of 5x. So that'll be dy dx. That's just a cleaner way of writing it. But so here's all of my examples of just how to deal with e to the derivative of e to any power. Let's do one where we have to do some implicit differentiation. So implicit differentiation with e to some x, or e to some power, is, let's try, so for example, if I said x equals 3e to the power of y, okay, how would I find the derivative of this? Well, the derivative of x is just 1. The derivative here is going to be 3e to the power of y, but then we have to multiply by the derivative of what's inside, which is y prime. So in fact, in this case, y prime is actually going to be 1 over 3 e to the y. I would just divide by 3 e to the y. So that works. What if we make the inside a little bit more complicated, such as maybe 7 equals e to the x sine y. All right, how would I do the derivative of this? Well, derivative of 7 is 0. the derivative of e to some power is e to the x sine y times the derivative of what's inside. Well, the derivative of what's inside is itself a product. It's x times sine y. So if I was going to do the product, I have to use the product rule, which is derivative of the first. Well, the first is just x, so that's 1, times the second, so sine y, plus derivative of the second, which is cosine y. But if I'm taking the derivative of cosine y, I need to take the derivative of what's inside cosine, which is just y, times the first. And there we have it. So we're done there. Now, if I needed to simplify this for just y prime, this gets quite ugly. But it's not bad. First off, yeah, so how bad is this? Oh, yeah, this is actually going to be kind of ugly. Not that bad. Okay, so what is this? This is 0 equals, I'm going to distribute this across. So this is ex sine y plus ex sine y cosine y times x times y prime. I just did this. For some reason, I switched the x and the y. There's not really a good reason to do that. I'm then going to move everything over and then divide. So if I move this over, I get negative ex sine y times sine y. So I move that over. And this is all multiplied by, so I'm actually just going to divide by e to the x sine y times cosine y times x. And that's going to equal y prime. Let's make this, let's pretty this, so here we got it. This is pretty ugly though. And we can make it pretty, quite a bit nicer. We notice, in fact, my e to the x sine y cancels. We also notice I have sine over cosine, which is tangent. And so this is going to be negative tangent over x. Negative tangent y over x. So y prime equals negative tangent of y. And there I have it. Done and done. So that's sort of a nice little quick example of a bunch of derivative of it. The last thing I want to point out here real fast, because this is just like a little trick that I see every once in a while, and it's an annoying trick because people fall for it, and it's just a trick. And I fall for it. So just pointing this out. So for example, if I had a function f of x equals the square root of x plus e squared minus 4x, and I wanted f prime of x, well, this is 1 over 2 square root of x, because that's the derivative of the square root of x, and the square root of e squared. Well, a lot of people think, well, the square root of e to some power is e to some power. But that's not accurate. It would have to be e to some x, right? It needs to be some sort of function. This isn't a function. This is just e squared. This is just a number, right? This is pretty close to 9. Well, the derivative of a number is 0. So remember, this would in fact be that. Okay? So just remember, if you get just an e to some number, this derivative is in fact 0. It's not just that function. So just be careful with that, right? So what's another one I see? Oh, every once in a while, like, and they'll throw in an e to the pi, right? Derivative, what's the derivative of e to the pi? Well, that's just 0, because e to the pi, they're both just transcendental numbers, but they are just numbers, so just be careful of that. But yeah, that's probably a pretty good little, hopefully that'll help you with your quiz while you're taking it, and now I feel less bad about. All right, good luck, and I will see you Monday.